Dr. Renato Molina has an interesting combination of backgrounds. He's both an engineer and an economist, which leads him to be specializing in environmental and resource economics. He currently holds a position as assistant professor in environmental and resource economics at the Rosenstiel School of Marine Atmospheric and Earth Science, with a whole host, a number of other appointments, including at the Abbas Center for Ecosystem Science and Policy at the University of Miami. His research revolves around pricing the resiliency of human and natural systems, with an emphasis on informing practical, sound, and responsible policymaking. He's currently involved in a huge suite of projects studying the economics of natural resource extraction and conservation, the impacts of natural disasters, and the value of climate adaptation. And also poking around that, according to his website, Renato also enjoys thrill-seeking hobbies such as flying airplanes upside down and jumping off helicopters while on a snowboard. And as much as I would like to question him further on those activities, I think our time would be better spent with Dr. Molina discussing his research into quantifying the impact and value of hurricane forecasts. So welcome, Renato.
Thank you. Thank you for that great introduction. And first of all, thank you so much for the invitation to give this talk. I'm very excited to hear what you think about it. This is a joint project that I have with my colleague and friend, Ivan Rudy. Currently is under review at the AJ, Economic Policy, the journal, one of the journals of the American Association of Economists. The title is The Social Value of Hurricane Forecast. And hopefully by the end of the talk, you will be able to understand why we named it that way. So this is perhaps not that of a relevant threat for the folks there in Canada, and particularly those in British Columbia. But tropical cyclones, or the way we know it here, hurricanes in the Atlantic, are a massive source of losses. So as most of you probably have seen in the news, right, like we have the fires right now, and basically the estimated toll that the fires in LA have cost right now are more or less, like on par of one hurricane or one of the big hurricanes that might take place every season. So that gives you a perspective of the massive threat that these storms have on the communities that are usually affected by them. And like even when we rank them against all of the other sorts of threats, including wildfires, right? This is data from the $1 billion event from NOAA, right? Like it's an order of magnitude difference in terms of like the overall historical damages that they caused. So this tells us that like this is an important threat. But as an important threat, like what can we do as humans and societies in the face of these really, really massive destructive sorts of events? Well, we can do many things, such as, perhaps we can build a dome around a city, and then like we'll be fully protected for future hurricanes. But it turns out the US is somewhat lagging when it comes to long-term adaptation, and that means like reinforcing households, perhaps constructing seawalls that might reduce the overall effect and destruction associated with storm surge and those investments of that nature. So given the lag in that end, like what we're left with is the option of do short-term adaptation. And short-term adaptation is the main sort of adaptation that we have, at least in the United States, to protect ourselves from the impacts of a hurricane, right? And that means evacuating, boarding doors and windows, perhaps building a temporary levee or a dike that could reduce the impact of storm surge, and so on and so forth, right? So how can we basically inform that adaptation is basically by knowing where a hurricane is going to go, right? Like we can not really respond immediately to the threat of a hurricane, right? So if, let's say, hurricanes were to span, like at random with no warning whatsoever, right? Like it will be very, very costly to move resources around, particularly because, like resources are limited in general, right? So our forecasts as the main tool behind adaptation have been getting pretty good. So the overall rate of improvement, depending on how you measure, right, since 2005, it's been about 40%. And that's pretty much aligned with, well, it fell a little bit short, but it's aligned with what the Congress envisioned the overall progress of the scientific tool that we have. So with that in mind, and then looking at the overall set that we have in terms of how these storms have behaved in the recent years, we can see that, yeah, hurricane forecasts have been getting pretty good, but also the storms are getting very, very costly, right? So we have Harvey, Ian, and Maria's, a couple examples that are recent, right? Like I'm not talking about Katrina, which is the most expensive one in recent years, but like all of those that I have in that slide there are very recent hurricanes that are all over $100 billion, right? The fire in LA, for instance, it's now being estimated to have produced costs that are around 150 billion. So this gives you a really shocking picture of the magnitude that these storms can have, and that happen a lot more frequently over recent years, right? And there is this expectation that storms are likely to get costlier and more frequent also in the future. So we can talk a little bit how that it's is statement that I'm very careful to make. So if there is any hurricane person here, please forgive me because I do understand there's a lot of nuance behind that statement. So with that on hand, as an economist, I'm left with the question of like, okay, so how useful are these things? Do they really generate value? If hurricanes are truly destructive and they basically cannot really predict a lot, or if we are already at the frontier of prediction, like are they still generating value and whatnot? So I partnered with Noah for this project, and we wanted to answer the basic question of like, what's the value that is provided to the public by funding this research program? So we're gonna break down this problem into 4 questions. The first one is going to be, does FEMA respond to hurricane forecast? The second one is, does the forecast accuracy matter, right? Because if it doesn't matter, then we can just go home and say, well, if we're right or wrong, then like it doesn't matter if we have this program. If it does, and spoiler alert, yes, it does, right? And if it does, like, can we actually backtrack or like basically infer the social value that they generate by being right and by becoming better? That's a really key important part of this study. And then once we develop that theory and we have the methods to basically derive that value, we will evaluate a specific program that was implemented in the United States with the objective of making the forecast better. And I will tell you all about it in a few minutes. So, the one thing that we need to um understand is a key part of this idea, and as an economist, this is one of the things that I spent most of my time thinking about, is if a forecast is consequential, right? If the forecast is consequential, then we have the link of causality that says you produce good information, you basically are able to take action based on that information, and then that action basically saves you money. So just to give you a little bit of background, this is more or less how a hurricane forecast works. So you will have something that is known as a deterministic forecast, which is aligned like that. So that's basically the track that the hurricane is expected to have. And those points that you see on this slide are basically where the center I is supposed to go, and there is some information embedded in those points, and that information is basically maximum wind speed at the storm center, right? So you can see here that the red, you guys can see my mouse, right? You can see here that the red track is basically what Katrina was supposed to, the track that Katrina was supposed to follow, and then in orange, the track that actually was followed. So building on those deterministic forecasts, right? Like what you create is what's known as an ensemble. And those ensembles are basically at a given point in time, you basically take the deterministic forecast and then you create a Monte Carlo simulation that creates a spaghetti map of 1,000 different ensembles that will track different tracks, even though it sounds redundant, with different wind speeds. And then you take the distribution of that forecast and you create what is known as the cone of uncertainty. So the cone of uncertainty is nothing else than a projection of the overall distribution of that ensemble of forecasts. And this characteristic of how the forecast is done is going to be key for our study here, that because it will allow us to basically estimate the social value of the specific product. I will note, however, that most forecasts basically follow the same procedure. The difference, though, is that the number of ensembles involved in making a prediction could vary depending on what you're dealing with. So, for instance, right now I'm working with the UK government to establish the value of their early warning flooding system, and that system basically doesn't have 1,000 ensembles. It actually works with 18. Right. So, any questions till now? Okay. So, with that, then you will create a swath of wind speed, right? So like with those ensembles, we'll tell you, well, the hurricane will go here. This is the speed that we'll have, right? And that sort of prediction takes into account many things, such as the surface of the land where it's going to go over, the overall climatic forcing that it has, and the path that it followed till the point when you're making the prediction, right? Because it's an autoregressive process, so you have to take into account the previous steps. So I was saying before, there is a deterministic forecast, there is the production of the ensembles, and then you create the slots that will give you a wind field probability distribution, right? And those, as I was saying before, are generated to create the cone of uncertainty. So that's the forecast that people might see on the TV, but then how does that drive action, right? So like on the individual level, right? Like people might see that forecast on the TV and they'll say, oh my God, I gotta evacuate. Oh, like this is gonna be bad, so I have to leave. But on the government side, how it works is a little bit more nuanced because you have the forecasting unit, which basically is actively trying to make the best prediction possible, and then they communicate to decision makers via what is known as the hurricane liaison team, and they basically are able to interpret all the output from the science to the decision makers and make a call and say like perhaps you should be closing the roads because there's going to be an impact that is significant here. And it's based on my conversation with the people involved in this decision making process, usually some sort of like back and forth, for instance, asking like, should I close this road or should I close this bridge or not? Like, should I evacuate the city or not? And the hurricane team basically creates that communication. So this tells you already that there is direct input from the forecast science into the decision making process. So that first question that I'm going to pose, right, is like, are these forecasts basically guiding what the government does, right? It should be a yes, right? And then the other side of things is what's known as the Public Assistance Grant Program, which is a program from FEMA that basically provides money to efforts that are aimed at reducing the impact of a hurricane and, for that matter, any natural disaster, right? Ex ante, meaning before it takes place, and also to recover, like public like infrastructure, public buildings, and so on and so forth. About 90% of declared disasters get funding through this program, with the federal government usually covering about 75% minimum of all eligible expenditures. So, for instance, let's say in the fire right now that is taking place, if the fire burns down library, then this program will basically build at least 75% of that library because it's a public building. So, right, so you can see, like, I don't know how this works. Well, basically, I have a quote here from Biden from 23, where there was a hurricane like incoming and was forecasted to hit, like the Panhandle, and then transition to Georgia and South Carolina. Basically, here's Biden saying like, I approve emergency declaration, right? And that means that FEMA is going to deploy resources. All of these actions need to go through a grant, right? So that's basically the decision-making process that's taking place in the background. So to answer the 4 questions that I told you I was trying to answer, we're gonna implement a mix of different disciplines, and that includes atmospheric science to replicate the path past forecast and also the actual storm. So we have to recreate the storm. There isn't really like a data set that tells you this was the overlay of the storm. So you have to recreate them themselves. And the same is true with the forecast. And we're also going to use economic theory to formalize the decision process. And we're going to use spatial econometrics to estimate the value of the forecast. So the data, as I was saying, basically now encompass the entire universe of hurricanes since 2005, plus all the tropical storms with damages above $20 billion. We also collected all the adapted actions pre-landfall, meaning we have all of the grants that were given from FEMA to all of the counties and states before hurricane basically made landfall, and also all of the grants given afterwards for recovery for all of the counties and in the face of these hurricanes, plus all of the shelter data that tracks deaths, property, and crop losses. And this is a little bit nuanced, but Shelters also tracks some of the public expenditures. There's some overlap in some entries, but basically we have the entire history from a public perspective, right? We don't really have information about individuals themselves, but sorry, I'm just checking the time. But we have information about what the government does, or everything on the government side of things. So to illustrate how we're gonna work with this thing, let's just look at Katrina. So here's the forecast of for Katrina, right? The dotted line where is where, you know, like what the forecast said it was gonna do, and the blue line is what it actually made. So if we now think about the forecast in terms of errors, right, we'll have two types of outcomes. One will be underestimate, and the other one will be overestimate. This heat map here shows you both, where like the blue color is the overestimate and the red color is the underestimate. So we can see here that we, at the time, right, the 72 hours ahead forecast, right, but grossly underestimated the wind speed that people in New Orleans were going to experience, right? So that's basically our main identifying variation here that builds on the models of both the forecast at the time and the realization of the storm. And we're going to have this information for 1, 2, and 3 days before the landfall of the of any given hurricane in that set that I was telling. Right, and here are some examples of the hurricanes that are present in this set. So we have Katrina, Sandy, Harvey, Irma, Florence, Michael. We have many more, right? And some patterns are worth noting from this data. And first of all, you know, like the average realized wind speed is about 10 meters per second, or, you know, like about 20 miles per hour. Precipitation in general is way harder to forecast than wind speed, and that recovery expenditures far exceed protective expenditures. And the reason why this is the case, you know, like it's interesting to think about the physics of precipitation relative to wind speed. Precipitation is usually driven by very, very micro and very local factors, while, you know, wind speed and the overall force of a hurricane will be driven by more macro global type of drivers. And that's one of the reasons why it's so hard to forecast with high precision the precipitation that a given storm might have. So circling back to our driving questions here. The first one, does FEMA respond to the hurricane forecast, right? So in the way in which we're going to identify this question is we're going to have a flexible function for spending, meaning how much protective spending the government does in light of the wind forecast and the precipitation forecast. And we include both in our estimated equation because they're correlated, right? And we're going to have also fixed effects for county, for storm, and for also different lead days, right? So this is basically our estimated equation. And we're going to keep track of the potential correlation, spatial and temporal correlation that usually plays these studies. So we're going to basically use Coulomb spatial errors using a radius of 400 kilometers, which is a lot more conservative than any of the previous studies before. So here are results from the paper. So what you can see is that if you are forecast a breeze, right, like you basically get no money sent your way. But as soon as you start hitting the threshold of hurricane winds, right, all the money starts flowing down your county, right? So as soon as you create a true threat of a hurricane, then money starts flowing in, and it's quite a lot. And this is not just an instrument, or like a mechanistic result of more populous or more economic prosperous states. Like the pattern basically is consistent once you start looking at protective spending normalized by GDP, and also protective spending normalized by person. So the answer to our first question is yes. It does seem like FEMA, at least via their protective expenditure grants, right, does respond as we will expect to the forecast. So the second question now is, does the accuracy of the forecast matter, right? Because yeah, you might be forecast to experience hurricane force winds, and then you will see the government responding to that information, but it doesn't matter. Does at the end, does that information matter at all? So we're gonna follow the same approach here, but it's gonna be a little more involved, because now we're gonna track the effect of the errors, right? So we're gonna have a flexible function that tracks damages and recovery expenditures. And then that's gonna be a function of our wind error, precipitation error, and then not only the error, but also the magnitude, right? One of the things that we want to avoid here is comparing, or like confounding more intense storms with more erroneous storms, right? We want to get the effect of the errors after controlling for the magnitude of the storm, both in terms of wind intensity and also precipitation, right? So we're going to have the same fixed effect structure here. And we're gonna also keep the same clustering approach. Give me 1 second. Okay, so we're gonna have the same structure here, right? So we're gonna have the same cone spatial errors up to 400 kilometers, which I iterate is the most conservative approach based on all the rest of the literature. And what do we get? We get the following results. So the way to think about this figure is you have two potential states of the world. On the one end, you have an overestimate. On the other hand, you have an underestimate, right? So thinking in terms of the error, negative errors will mean an overestimate, and positive errors are underestimate, right? So when it comes to wind, overestimating the wind basically doesn't really save you any money, right? It doesn't. It's not beneficial to tell someone you have to prepare for a category 5, and then a category 5 takes place, right? What it is costly, however, is when you underestimate, meaning you go and tell someone you're gonna experience a breeze, but you end up experiencing a category 5 hurricane. That is extremely costly, right? So, and for instance, if I were to show you the log results, you will see that basically all the damages associated with underestimation basically grow exponentially, right? So overall, like a 10 meter per second under forecast will cost about 250 million relative to a perfect forecast. And what this does, right, is telling you that the information and the quality of information is consequential. Giving bad information to the government and individuals in this case, right, is basically very costly when we're thinking about the value of the forecast. More importantly, and along the same lines as in the previous case, right, this result is not driven by the size of the economy of a given county, or by how populous a given county is. Like the same pattern arises in all of the scenarios that we're covering here. So we answer first question, is the hurricane information consequential? Then we answer the second question, which is the accuracy basically that doesn't matter, right? So you have a dynamic of, like the input is important and the quality of the input is also important. So now we want to establish what is the value of those characteristics, right? And to do this, we have to now abstract a little bit from the empirics and implement some theory. So I'm going to try to make this very simple, and just imagine you have a social planner, and the social planner basically faces damages from a threat, in this case a hurricane, right? And that hurricane creates damages as a function of two arguments. One is the strength index, and the second one is the adaptation, right? So meaning the stronger that threat is, the more damages you're going to experience. The more adaptation you engage in, the less of those damages. So that function D increases in X and it decreases in A, right? And then what we're also going to assume is that there is some cost of adapting, and that cost is strictly increasing and convex, right? Meaning that adapting a lot is increasingly and ever increasingly more expensive, right? So the tricky part here is that the agent making the decision, the social planner, does not have access to the perfect information about the intensity of this threat, and in this case, intensity of the forecast, but it has some signal with noise, right? And we're gonna define then an error component, which is the difference between the realization, the realized intensity and the signal that the agent gets. And we're gonna assume basically a normal distribution with mean mu and standard deviation sigma. And it turns out that in the data, if we look at how the errors are distributed, this is a very plausible assumption for the hurricane problem, right? So the planner's objective is to basically minimize the cost. And in this case, you can think of, like the social planner is trying to reduce all of the capital damages, but also, like how many people die, right? So, but because they don't know what the actual intensity is going to be, they have to work in expectations. So they have to reduce the minimized expected cost. They have to reduce the expected cost rather than the actual cost, right? And that is subject to not just the expectation of cost, but how costly adaptation is, right? So we're gonna name this function C here as the optimal cost, meaning it's already minimized, right? So let's say you have some signal here, squiggly X, that the intensity of a hurricane is going to be category 3, then you take action, right? And so as you minimize the expected losses from that hurricane category 3, but also taking into account that any adaptation you take is expensive, right? So the total derivative of that optimized function with respect to the uncertainty of the forecast, which is capturing that standard deviation, is the value of improving that forecast, right? In other words, what is the reduction in the optimal cost if you were to have a signal that is less noisy? And it's all embedded in that the sigma, right? So just to reiterate, the value of improving the forecast is basically the change in the optimized cost as I change the uncertainty associated with that signal that I get. So, and here's our main contribution here, is that we show with theory, right, that total derivative, it's basically the following. It's 1 over the standard deviation to the power of 3 times the covariance of the damages and the mean error squared, right? And for those of you that are familiar with regression theory, this is a regression, right? That is basically what a regression is. So if we, like replace those terms with the formula of a regression and then solve, we basically get that this total derivative, right, is going to be 2 times the standard deviation times the coefficient of running this regression, right? Pretty simple and pretty neat, actually, right? So again, beta 2 is going to be the coefficient associated with regressing the cause of a hurricane, right? Damages and recovery against the square of the mean error, right? That's the error, that's the mean. And then you square that regression 2 times the standard deviation is basically the value of making the forecast better at a given set value of sigma, right? And so this result basically indicates 2 things that are important. One, that improving the forecast is valuable, meaning there is that total derivative is greater than 0 if a given forecast is uncertain, right? Or if that threat is very expensive, right? So meaning if I have, I don't know, one way to think about it is if I have a, like an asteroid about to hit the Earth and, like I get a noisy signal about it, right? Like that's going to be a very, very expensive shock. So like it's really valuable to make the forecast of where that asteroid is going to hit, like really, really, really high. Questions up until now? All right, I think I'm right on time. So taking the theory to the actual empirics, it's gonna, basically follow the same approach. We're gonna have a flexible function of damages, and then we're gonna break down everything in bins. So our analysis, just as I was showing you before, is everything basically non-parametric, just to really capture what the dynamics are of like this problem. So in this case, we're gonna have bin for wind forecast, bins for precipitation forecast, and then we're gonna track the mean square error for all wind and precipitation. And we're gonna be focusing on precipitation here. That's the main measure of interest. The clustering approach is gonna be the same as before. We're gonna keep having the same fixed effects structure that we had before, in which we control for counties and also for state storm, right? And our results of interest here is, again, that coefficient there, right? Which will tell us the value of one standard deviation reduction in the wind forecast uncertainty. So here where the interesting results come, right? So this table here is showing you the result of that regression, keeping track of that coefficient here, right? That's the coefficient associated with that parameter of the theory. So, and I'm showing you here the result for a wide array of different, like fixed effects, right? Controlling for different things. So what we have here is that it's fairly constant, right? If I throw everything I have in this regression, I get the same, more or less the same result. Here's the tricky part. Once I categorize those results between hurricane and sub-hurricane forces, meaning I want to differentiate between counties that were, like exposed to actually hurricane winds rather than those that were experiencing a breeze, right? What is the value associated with making that forecast better? And I get a really strong result here, which is basically there is no value if, like hurricanes were always to be a breeze, right? Where all of the value comes from is from being able to forecast accurately hurricane force winds, right? So if I look at my sample, right, the overall standard deviation of the forecast, remember when I was telling you the story of how the forecast is produced, right? I get this distribution of wind over space, right? That standard deviation for all storms in my sample is about 1.41, right? So if you then bring that result and do the 2 times 1.41, then that's where you get about 16 million per county. And if you break down by year, basically the rate of improvement of the forecast since the start of our sample, 2005, is about 500,000 per county per year, right? Which is quite a lot. So now that we have that result, and that's, perhaps you might be interested in that result overall, you can say, well, this is very valuable. But, let's say you have Ted Cruz, who then will ask NOAA, right? Like, why are my taxpayers funding this program? Like, yeah, I know it's valuable. It provided some useful information, but I need to understand how is this benefiting the people that I represent. And this brings us to the last question that we are trying to answer here, which is what is the value of historical forecast improvements? And for that, we're going to use a very neat policy change. So in 2005, after the Hurricane Katrina hit and like devastated the United States, basically the Bush administration came up with this idea to create, mandated by Congress, what is known as the Hurricane Forecast Improvement Project, which, you know, like a few years past, this transitioned to a program, right? It's no longer a project. But quoting straight from the news here, the project seeks to improve hurricane track forecast accuracy by 20% for days 1 through 5 by 2013, improve hurricane intensity forecast accuracy by 20% for days 1 through 5 by 2013, and extend the lead time of hurricane forecast out of day 7. No, that's it, right? So if you recall the numbers that I was giving you at the beginning, basically it fell kind of short, but still did pretty good, right? It almost came close to that goal of killing or reducing track and wind intensity errors by 50% in 10 years. Now, it came very close, and you know, like for that, we should be impressed. Like it's pretty, you know, shocking how good of a performance that program had. And what way or what better way to tell that story than showing you the actual figures? So here are the errors pre the implementation of that project, and here are the arrows in blue of the hurricane forecast after the implementation of that project. And if we track these things, right, it becomes pretty obvious that something happened there. Well, we don't have a way to causally identify what happened there. I think it's pretty safe to assume that, you know, like perhaps it has to do with the hurricane forecast information project, right? I mean, like if we look at this set of forecast here, right? Like the last 10 forecasts had less error than anything that ever happened before, at least in our sample, right? And that says a lot. That says a lot about, you know, like the power of you know, believing in science. And I think that's one of the main lessons here, right? An order of magnitude reduction in mean error reduction after the project was implemented and, you know, created. So if I take my formula, then I can have a really cool thought experiment. I can use this trend and project it forward, right? And say, well, what if instead of the actual rate of improvement, we just follow the pre-trend, right? So I'm gonna say, assuming that all of the years after 2007, when the actual project started, right, would have followed the same trend, that red line, then what would have been the difference in cost? And this is what this figure shows. It shows the value of having a better forecast relative to just continuing that pre-project trend, right? Overall, it's the improvement since the project was implemented. It's been about 1 standard deviation in wind intensity spread, and that's quite a lot, quite a lot. And if we bring that in terms of money, right, the average value generated since the project was implemented is about 2 billion per storm, right? Total estimated damage is about 60 billion. In percentage terms, that's basically 20% of the total damages of the storms since that project was implemented have been avoided because the hurricane got a lot better, right? And then when you bring those numbers in perspective with the actual cost of running this thing, you know, like the total cost of running the HFIP since 2007 has been about $300 million, right? So, you know, like a massive rate of return for what you invested in terms of how much money you saved. The total running No, the total cost of running the entire federal weather forecasting is about 1 billion, 1/3 of the NOAA budget. So still, you know, like the rate of return of this thing is impressive, and if not, maybe unparalleled, right? So this brings us to basically the last part of this presentation, in which I had to give you the usual disclaimer in which you could ask, well, are these results biased by some of the assumptions you made? And I can tell you that we have a ton of robustness tests, additional fixed effects. We also restrict all these samples to states on the Atlantic and the Gulf of Mexico. The results are basically very, very robust. We have different specifications for forecast errors and damages. We have different, we also control for spatial duration of the forecast, or sorry, the storm and where it takes place. We also have a test in which we basically look at how much individual hurricanes are driving the results. This used to be a bigger problem when we had only major storms, but after we basically increased the sample to include all of the hurricanes, basically the universe of hurricanes that have affected the United States since 2005, this is not that much of a bigger problem anymore. We also, like have different cutoff calling spatial errors, and we still get the same results up to 800-kilometer radius. We also explore, like different and potential heterogeneous effects of forecast errors, though there is some evidence that, like some of the errors might affect different people differentially. It's usually higher income people, which is, something to keep track of. It remains to be seen if with the recent trends in hurricanes and how they basically, like continuing to be strong and destructive way farther inland, how will that affect in populations of less income? But like there's some future work to be done on that area. So overall, I've spent all these minutes trying to tell you a few things. One, that forecasts are far from perfect. I just told you that it fell short from the expectation. But when it comes to their consequentiality and the effects that they have in terms of driving adaptive behavior, they're very valuable, right? They basically do value they do encourage action, and the quality of the forecast also matters, right? So when people are listening to what the Weather Channel is saying, which is basically a regurgitated version of whatever no one is putting out, right? That has value. When the government officials are paying attention to what the forecasters are saying, then that has value, right? It's important to know that not all errors are the same, and that underestimating the intensity of storms basically results in the highest cost. That result is intuitive, and I think humbly that is one of the most powerful results of this paper. Basically telling us the story that like you gotta be careful if you have a process in which the climate regime is transitioning, right? In which storms are likely to become a lot less predictable on one end, meaning that you're going to be perhaps worse off predicting storms that intensify really rapidly and create these really, really aggressive wind forces, then, perhaps it's worth thinking very carefully about how to reduce those damages, because once you start airing the forecast, you're going to be facing really, really high costs. Not all hurricanes are the same. Again, like in the nature of the storm matters. So the moment you start facing a regime shift in which storms are a lot stronger, then it's gonna become even more valuable to have good forecasts, right? Like the stronger the storm is, the more valuable it is to have a proper forecast, right? And finally, to wrap it up, and I think I am within the time framework. I always finish this, talking about this project in terms of, like what an economist will think about this. And the way I come from is this is a really good public product. If you really tally the cost and benefits, it's perhaps one of the best public policies, like that the United States has in place. And it's effective, right? And has been done, like properly. And this basically is a segue to say, what is the true value here? The true value here, is the outcome that is generated by research and science. And that is not the scientists, like working for the sake of humanity's welfare, but also, like all the private parties are producing technology that is used to improve the forecast. All of the like researchers that are getting grants that like are aimed at improving like the understanding of the physics at the micro level, right? But it's also driven by all the private companies that are producing like these massive supercomputers that are making the forecast more precise. It is also like paid by like politicians, perhaps forgetting the petty fights when it comes to actually thinking about what the science is saying and the implications on the ground. So overall, I think this project contributes to that dialogue, contributes to that conversation in terms of how to think about public products that foment, adaptation in the face of climate change. And my contribution or our contribution here is basically based on how information is basically a huge part of adaptation. So to wrap it up, this project was like aided by several people. Here, some of my students, some of Ivan's students, some research staff that also it's collaborating with us over the years. And yeah, that'll be all. Thank you for paying attention to stuff. And yeah, I look forward to your comments or questions.
Okay. Thank you very much. Just to remind our audience that is, well, everyone's online, that you can either paste your questions directly into the chat or raise your hand, and we'll try to get to you. I'm going to jump in right away with maybe I might classify this under a practical question. So where does the increased value of better prediction come from? Is it allowing FEMA to spend resources more targeted, or is it on the people side of preparing for the hurricane?
Yeah, that's a great question, and that is confounded. I mean, if you think about how basically the government takes action, their action also drives people's action, right? Like the government says, okay, this kind is going to be hit, so we need to deploy resources. Perhaps we need to bring the National Guard. Perhaps we need to like set a temporary shelter. We need to evacuate people here, and they will release a warning, right? Like, and that already drives people's behavior, and that, for instance, will cause people to actually take it seriously, to board, right, to get sandbags and protect the property from flooding, and all of those actions that like that are driven, in my argument here, is that the forecast causes the government to react, but also people, which unfortunately we're not able to track. And we try to look at how like different purchases vary depending on what the forecast was, but like the data right now, or when we were trying to do it, wasn't up to the standard in terms of resolution. But we do see responses at the individual level, right? Even with the messy data that we had at the time, it wasn't really that clear. But that's basically what I'm trying to say here. Yeah, we can clearly see responses on the government side. And my argument is that when the government responds, individuals also respond, either because the government is responding or because they have access to information that is triggering the government to respond.
Thank you very much. William, do you want to go ahead and ask your question, please? William, go ahead. Okay. Oh, he can't unmute.
Oh, yeah, I can do it now. Sorry,
Okay,
I
there we
wasn't.
go.
Thanks, Renato. Really interesting talk. And a question is, I mean, I see a lot of analogies on these extreme events, weather events, to the oceans and fisheries, which a lot of us work on. For example, heat waves impacts on ecosystems or fish stocks. And I think, I mean, the predictability of heat waves and their impacts are nowhere near to hurricane forecasts. So I'm wondering how that, like a much bigger level of uncertainty in predictions would affect the counting of the costs and benefits of improving the prediction program. I mean, there are colleagues who work a lot on trying to improve better predictions of how extreme events impacts fisheries or ecosystems. But then, as I said, I think the margin of error is much bigger compared to hurricane forecasts. So I'm just wondering how that play a role in the estimations of the benefits of this kind of research and the program in predicting the extreme events.
Yeah, thank you. That's a great question. And it's good to see you, or like virtually see you. So the answer to that is a little bit muddled. And this is the reason why. The problem with heat or marine heat waves, and in my view, is that is a less one serious shock as a hurricane, right? So for instance, like you have a process in which you have, let's just think of the analogy of a boiling pot, right? So you set out the heat and like, yeah, there might be some fluctuations, but like it's something that is heating, and then it reaches a boiling point, and then you experience these damages. So when you have a trend, the value of predicting what's going to happen at the end of the trend, right, is not that valuable. Do you see the point that I'm saying? Unless, like, if you see that the trend is basically telling you all the information you need about the consequences of something, you already know the trend, right? If you have extreme events in which the trend is muddy or like not that clear, right? Then there is a lot of information, a lot of value of knowing what the actual trajectory is, and also information about the damages. So I think there are two important questions here when it comes to all the sorts of forecasts and trying to understand how, like a change in climatic regime can affect, like certain systems, and the value that the systems have for us is, one is, if all the information is embedded in a trend, then perhaps the value of understanding the system and predicting what the changes are is embedded in understanding the trend. If we don't know what the consequences can be, in terms of, like what happens when we pass a certain threshold, then, like the value of forecasting when that threshold is, or like what that threshold is, what the consequences of the threshold, that's when you start creating value. So I guess, like I don't think I'm answering your question fully, because the analogy with hurricane is a little bit different. Like a hurricane, basically, you kind of know that you're gonna suffer some impacts. Those impacts come in a certain way, and like you can protect against them if like where it's gonna go, right? And that is proxy via the wind speed. For a heating ocean, when like maybe you pass a regime shift and then there are no species to fish anymore, or your corals die, right? Like the value of knowing something about the system, right, can come either from knowing when that regime shift is going to happen, so as you prepare, or basically trying to understand what the trend is, so then you don't have to basically forecast the date, but you can just basically understand better the system.
Andrew, do you want to go ahead and ask your question, please?
Yeah, thanks for your talk. My impression is that weather forecasting is getting better and better. And I'm wondering, from your perspective, are we reaching the asymptote in terms of improving the predictions? Or what do you see in your crystal ball for the future? So I assume that hurricane forecasting is on par with weather forecasting.
Yeah, that is an awesome question, and it's something that I've discussed with my colleagues working on hurricanes all the time. They seem to think that we are reaching the asymptote for hurricane predictability, that we're getting closer and closer. But my argument to them is that perhaps that is true with the past regime of hurricanes, right? Like now that we've seen hurricanes are intensifying a lot faster than they had in the past, that asymptote might have been moving a little bit related to their assessment, right? So perhaps we are really good, and the problem, and I'm gonna perhaps do a really poor job explaining where the issues here, because I'm not an atmospheric scientist. But the problem with rapid intensification can, like be explained. Imagine like in Chile, we have a tool that is, or like a toy that is called a trompo, right? So when a trompo basically spins, at a certain speed is somewhat predictable, right? Like a trompo is like a thing that spins, you like throw it and pull a line and then it spins. But when it hits different, different surfaces, and then the trajectory becomes less predictable. And that's basically what happens with intensification, rapid intensification, that as the storm basically fills up with warmer water closer to the shallower areas, and then it hits a different substrate, which is land in this case, right? It becomes a lot more unpredictable because it's both intensifying, of course, right? Like the speed at which it's spinning and which is generating wind increases, but also the surfaces which interacts, right, are introducing uncertainty in it. So if that process is to become a lot more frequent for a lot more storms, then like I would say that there is still space to keep improving, and because of that, there is still space to keep generating value from further improvements. I'll say, however, that the value of making the forecast better, as you perhaps suggested, is not infinite, right? There is a point in which it doesn't really make sense to invest more in a forecast, and perhaps it will be better to invest in different resources. In an earlier version of our paper, we actually test if we are past that point or not, and based on our results at the time, we can confidently say that we're still in the area of increasing returns, meaning it still makes sense to make the haircuts a little bit better. Whether that's true in 5 years, remains to be seen.